Let's take a look at an example of linear programming. Now, don't get excited about the title. We won't be programming in computers. When we talk about linear programming, we're simply referring to the process of taking various linear inequalities and describing an everyday situation and finding the best possible value under those conditions. A common example would be taking the limitations of labor and materials, actually called constraints, and determining the best production levels for maximum profits. That actually be called optimization, which is very closely related to linear programming. Most real-life situations involve hundreds of variables. In this section, we'll only be dealing with a strictly the two-variable case. So let's say we're given the following equation. We're given z equals 5x plus 2y. And let's say this could be a cost formula. X could be labor, y could be materials, and we want to know how much is going to cost. Something like that. And we're given the following system of linear inequalities. We're given 2 over 3x plus y is less than or equal to 4. We're also given x plus y over 3 is greater than or equal to 2. And we're given x over 3 is minus y is less than or equal to 1. This is a system of linear inequalities that we'll now call constraints. This is a formula, maybe a cost equation, and this is called constraints. What we want to do is we want to find the maximum and the minimum value for this equation given these constraints. All right, now I'm going to show you how we're going to do that. First of all, we're going to start out by using what we know. We know that we're going to use this system of linear inequalities, and when we graph these linear inequalities, we're going to get a solution that actually gives us a region. So let's go ahead and first point these in slope-intercept form so we can graph these. So let's solve each of these inequalities for y. Let's start off by the first one. We subtract 2 over 3x from both sides. We get y is less than or equal to minus 2 over 3x plus 4. All right. So far, so good. Let's take a look at the second one. This is our first linear inequality. Our second one, if we subtract x from both sides, we'll get y over 3 is greater than or equal to minus x plus 2. Let's go ahead and multiply the whole inequality by 3. That'll cancel that denominator, giving us y is greater than or equal to minus 3x plus 6. That's our second linear inequality, called a constraint. All right, let's look at the third one. If we subtract both sides by x over 3, we get a minus y is less than or equal to minus, let's separate our variable and our fraction. We have 1/3 x plus 1. Let's go ahead and divide through the inequality by minus 1 so we can solve for a positive y. These two negatives will cancel. These two will cancel. All we need to remember is flipping our inequality sign from less than or equal to greater than or equal to. We're doing so because we divided by a negative. We should know this by now. So we have a positive 1/3 x and a minus 1. And this is our third constraint. Okay, so we have a cost formula and we have 3 constraints. So let's go ahead and graph these. So we're going to scroll down for a bit and go ahead and graph these constraints. So we have the y-axis right here. We have the x-axis right here. This is the positive direction for the y-axis, and this is the positive direction for the x-axis. We should be very good at graphing, actually equations and inequalities by now, but this is going to be graphing inequalities, and we know that when we graph a system of linear inequalities, we're going to get, the solution is going to be a region and not just a point. So let's go ahead and plot the first one. So this purple line, the first one, if we plug in 0, y is going to equal 4. So this line is going to cross the y-axis right here at 4, and it has a slope of minus 2 over 3, so it's going to drop down 2 and go over to the right 3. And we simply connect these 2 points with a solid line because it's less than or equal to. So it's going to, the possible solution will be on every point on that line. Every point is a possible solution for the system of inequalities. Once we narrow it down to a region, it'll actually make a border, which we'll talk about that in a second. So here, this blue equation, we're going to plug in 0 for x, which gives us y equals 6. which occurs right here. It's going to cross the y-axis right there. It has a slope of -3, so we're going to drop down 1, 2, 3 and move to the right 1, which is right about there. And those two lines intersect right there, which that's very important to know. We'll talk about that in a second. We're just graphing our inequalities right now. We know how to do this. And let's go ahead and plot the third one. So we plug in 0 for x. We have y equals a -1. This point right here has a slope of a positive 1/3. It's going to give us this point right here. And we're going to have a greater than or equal to sign, so it's going to include all the points on this line. We're going to have a solid line going in both directions infinitely, excuse me. Okay, so now we want to find the solution region for these three constraints. So we know that we want the area that's less than, that's under this purple line, that's greater than this blue line, so above this blue line, and that's greater than this green line above it. So we're talking about this little solution, this little region right here. Looks like a triangle. This is our solution region for this given system of inequalities, including every point in between the lines and also including every point on the three lines right here that's bordering this triangle. Okay, so we're going to switch notation right here. This used to be called the solution region. Well, we are going to call this, since we're talking about a particular topic now called linear programming, this is going to be called the feasibility region. And I already misspelt it. I'll get this right. Feasibility region. It's just a fancy word for every point in here is, I guess it's just feasible to be the solution to this cost equation. Okay, so this is the feasibility region, and one of these points, including the points on the outside, is going to be the optimal solution for this cost equation. We're going to have the maximum and minimum value occur somewhere either in this feasibility region or on the perimeter. Okay, so now that we've got this plotted and graphed, the feasibility region, what it does is it contains all possible solutions to our system of inequalities, or constraints if you want to call them that. But what we want to find is the optimal solution to this equation right here. This is the cost equation. Now, somebody a long time ago that was really smart proved the following, that the maximum and minimum values for this cost equation, or this equation right here, occurs at one of these 3 points where the constraints intersect. The constraints intersect at these 3 points. So we don't have to plug in all the values, all the possible values in this feasibility region. First of all, we wouldn't be able to because there's an infinite number of points in here. But we're only concerned with these 3 corner points of the feasibility region. So let's start there. There's 3 of them here, and to find them exactly, we're going to need to write and solve 3 systems of linear equations, which we should be very good at by now. Notice these are going to be equations and not inequalities, since we're looking for an exact point and not a region. So we're going to set up these linear equations in the next video. We're almost out of time, and then we'll end up getting the maximum and minimum value for this cost equation given these constraints. So I'll see you in the next video.